In this lecture, we are going to characterize a minimum point of a continuously differentiable function of several variables. In characterizing a minimum point, we will involve the first order partial derivatives of the function, and thus we name it as first order characterization of a minimum point of a function of several variables.
Well, if we revisit the last lecture, then we will find that we started our discussion in the topic of local, global, and strict minimizers. The notion of strict minimizer was required to resolve an anomaly in the definition of local and global minimum. The anomaly was a local minimum can possibly be a global maximum of the function. To resolve this issue, the notion of strict minimizer was required and defined. Well, afterwards we were trying to identify some existence of a minimizer for a given unconstant optimization problem. Towards this, we have discussed two particular results. Those were named as existence theorem 1 and existence theorem 2. In the existence theorem 1, it was essentially the Weierstrass theorem or extreme value theorem that says that if a function f is continuous on a closed and bounded set, then the function must have a global minimum and as well it must have a global maximum in the given closed and bounded or compact set. And afterwards, in the theorem 2 on the existence of minimizers, we have defined the notion of coerciveness, and we have seen that if a function f is coercive in the entire Euclidean space, n-dimensional Euclidean space, and that function, if it is continuous, then the function f must have a global minimum in the entire n-dimensional Euclidean space. And afterwards, we have given a few examples on coercive functions. We have seen that a linear function can never be a coercive function. And later on, towards identifying characterizations of optimum points, I mentioned that we require the notion of descent directions. At a particular point x bar, a given direction d is a descent direction of the function f if the function decreases at least locally along the given direction d from the point x bar. And then later on we were thinking to characterize descent direction. Time was off. In today's class we will continue our discussion in the descent direction, where we will start our lecture with first order and second order characterizations of descent directions. As you all know by now, by first order and second order conditions, we mean some conditions which will involve the first order and second order derivative respectively of the given function. So at first let me give you a result on characterizing descent directions of a given function which is known to be differentiable. And towards this, as I have hinted on the last day, along the given direction d at the point x bar, if the directional derivative is negative, then obviously instantaneous rate of change along the direction d for the function f at the point x bar is negative, which means that the function must be locally decreasing in nature along the direction d from the point x bar. And that is the result, the first order characterization of descent direction, which says that if the given function is differentiable in a neighborhood of a point x bar and for a given direction d, the directional derivative along d of the function f at the point x bar, then D is a decent direction of f at x bar. Let us now try to prove this result. Now for this result we will require to call Taylor's first order expansion. As the given function is differentiable in a neighborhood of x bar, therefore by Taylor's theorem we have f of x bar plus alpha d is equal to f of x bar plus alpha d transpose gradient of f x bar plus small o of norm of alpha d, right? As norm of d is constant because d is a given direction, and therefore we can just write it is small o of alpha. Here we are obviously assuming that this x bar plus alpha d is belonging to the neighborhood, let's suppose, let me precisely write, in a neighborhood b delta of x bar. Fine. So by Taylor's theorem, for all alpha greater than 0 such that x bar plus alpha d belonging to the neighborhood b delta x bar, we have this, right? And once we have this, then we know that we can just write from this equation, as alpha is a positive quantity, let us divide on both the sides by alpha, and we will get f of x bar plus alpha d minus f of x bar times 1 by alpha is equal to gradient f x bar transpose d plus small o of alpha divided by alpha, right? And obviously we are assuming here alpha not equal to 0, and again we have assumed it alpha greater than 0, and thus there is no problem, as limit alpha tends to 0 plus small o of alpha divided by alpha is equal to 0. Now if we apply the epsilon delta definition of limit for a function, then by choosing epsilon to be modulus of gradient fx bar transpose d, which is obviously a positive quantity, for this epsilon we must have a delta greater than 0 such that you have this small o of alpha divided by alpha, this function minus the limit 0 is less than epsilon for all alpha belonging to 0 to, let me write here a different delta, otherwise this delta might be mixed up with b delta in the hypothesis. Anyway, so I am choosing delta bar then. This is your epsilon delta definition of limit. Due to this limit is equal to 0, we have this inequality being true. And hence we note that this implies, as this epsilon is positive quantity, and therefore here from here we can just write alpha divided by alpha. We note that as this quantity inside this absolute value is negative, therefore we can just write epsilon is nothing but gradient of fx bar transpose d negative of it, right? And this has to happen for all alpha belonging to 0 to delta bar. Fine. And once you have this, then we know that you have small o of alpha divided by alpha plus gradient of alpha x bar transpose d is less than 0 for all alpha belonging to 0 to delta naught, say, where delta naught is equal to minimum of the delta in the hypothesis and delta bar in the epsilon delta definition. we name this as 1 and this inequality as 2. Then from 1 and 2, what do we have? From 1 and 2, we have 1 by alpha f of x bar plus alpha d minus f of x bar is less than 0 for all alpha belonging to 0 to delta naught. What does it imply? It implies f of x bar plus alpha d is less than f of x bar for all alpha belonging to 0 to delta naught, right? And this is what you require. This is the definition of d being descent direction at the point x bar. Fine. Now, what if your directional derivative along the direction d is equal to 0? In that case, can we have a characterization? Yes, we have, and that is the next result, which is the second order characterization of descent direction. With the help of the Hessian, we will be able to identify a characterization, and that's why this characterization is named as second order characterization of descent direction, which says that let f be twice differentiable in a neighborhood of x bar, and this x bar is obviously a point in Rn. Let this and also let the direction is given and a direction which is non-zero direction is given. For a zero direction, it does not have any essence. In the definition of descent direction, we always think that d is a non-null vector. Otherwise, you don't have any precise direction. Anyway, so assume that the directional derivative of the function along the direction d is equal to 0, and you have Hessian at x bar for which d transpose Hessian d is less than 0. Then we can prove that d is a descent direction of f at the point x bar. Fine. For the proof, it is again in the line of the proof for the first order characterization. We will here also use the Taylor's theorem, and by Taylor's theorem, let me just hint out, it is similar to first order characterization, and that's why let me just give you a hint. Here we note that if we consider the second order approximation of the function f by the Taylor's theorem, then we will have f of x bar plus alpha d is equal to right. We know that second term here, this is equal to 0, and here this quantity is negative, so on both the sides you divide by alpha square and you have a small o here, and small o of alpha square divided by alpha square is equal to 0, in the same line of logic as previous in the first order characterization. As this is less than 0, you'll be able to find the proof. Let me skip complete writing here. Now let me move ahead. With the help of the first order characterization, we can find a necessary optimality condition, first order necessary optimality condition. And in optimality, by that we mean here a minimality in our course. And therefore, let me here write out the first order necessary optimality condition, and also will prove this. It says that if f is differentiable at a given point x bar, and if you have that the point x bar is a local minimizer of f, then you must have the gradient vector at the point x bar a null vector. Fine. Now, why is this so? This is very easy to observe from the first order characterization of descent direction. Because with the help of that first order characterization, you will be able to prove this result by the method of contradiction. So, in the method of contradiction, if possible, let gradient of f x bar is not a null vector. If it is not a null vector, then note that for d, if you choose that minus f of grad, then this d is a descent direction, right? Because with this d you have the directional derivative given by negative of norm of fx bar square of it, right? And therefore it is a negative quantity. So by first order characterization of descent direction, there exists a delta greater than 0 such that you have f of x bar plus alpha d is less than f of x bar for all alpha belonging to 0 to delta. This inequality then means that x bar is not a local minimum, which is contradictory to the assumption. And therefore, our assumption was not valid, and hence the result is followed. Fine. Now, here, after this result, although it is simple to prove, but there are many things which can be extracted from this result. And not only extracted, but those things are really important to know. The first note that I would like to mention here is the following, that this result is really a necessary condition for optimality. It is not a sufficient condition. For this, we consider an example. Now, for this, for instance, you consider fx is equal to a function of one variable, let me give x cube. And for this function, we note that the derivative value at x bar is equal to 0, but x bar is equal to 0 is not a local minimum. It is a point of inflection, right? If we recollect the graph of the function x cube, then we note that its graph is something like this, right? And here we note that 0, the point 0, is neither a local minimum nor a local maximum. And these such points are called as point of inflections, right? And not only for function of one variable you have one example, but also you have example for function of several variables. For instance, another important example. Why important? Because from this example you will have a new definition called saddle point. So consider f of x1 x2 is equal to x1 square minus x2 square. Fine. And for this function, you note that if I take x bar to be the null vector, then you note that the gradient value at the point x bar is the null vector, no doubt, right? And what about the point x bar? Is it a local minimizer? It is not really a local minimizer. Why it is not a local minimizer? We can mathematically refute it. That you consider any neighborhood for any delta greater than 0. In the delta neighborhood of the point x bar, we know that we have a point delta by 2 0 belonging to the delta neighborhood of the point 0. We have these as well. You have 0 delta by 2 belonging to the b delta neighborhood of the point x bar, such that you have at the point delta by 2 0, the function value is bigger than the function value at x bar. Fine. And therefore obviously what happens, the point x bar is not a local maximum. For the point 0 delta by 2 is less than f of x bar. And therefore, evidently, the point x bar is not a local minimum. And not only that, at the point x bar, you have the phenomena that it is neither a local minimum nor a local maximum. Such points are called as point of inflections or saddle point. So let me define precisely what do we mean by a saddle point. For the definition, we define saddle point for the differential functions only, and therefore we start with letting a function f of r into r be differentiable and x bar is stationary point. But what do we mean by a stationary point? By a stationary point, we mean a point for which the function f has a station. What do you mean by the function f as a station? As you all know, in station, usually trains halts, right? That means if the velocity or the derivative value is equal to 0, then in that case, we call the function is having a station because it halts to improve or to degrade its value. It halts only on a particular constant value, and that's why it is called a stationary point. So a stationary point for a differential function is a point at which the derivative value is equal to 0. A stationary point x bar is called a saddle point if in every delta neighborhood of x bar there exists x delta dash and x delta double dash such that f of x delta dash is less than f x bar and f of x delta double dash is greater than f x bar. That means the point x bar is neither a local minimum nor a local maximum. Fine, and this has to happen for every neighborhood. In every delta neighborhood, this is very important because if you have one neighborhood, let's suppose you have one neighborhood of the point, let's suppose this is my x bar location, and you have one neighborhood in which you have found one point x dash here and another point, let's suppose x double dash here, such that these two inequalities are holding true. But that will not lead us to say that the point x bar is a saddle point, because you might have a smaller neighborhood, in which the function f is having a local minimum. Fine. So if you have found only one neighborhood, one delta value, and accordingly one delta neighborhood for which you have found x delta dash and x delta double dash satisfying these two inequalities, that does not imply the point x bar is a saddle point. Fine. So please be careful here that for every delta neighborhood you have to provide x dash delta and x double dash delta satisfying these two inequalities, right? Fine. So let me explain this definition with one more example so that the idea will be clear. Let me take an example. This example was given by an Italian mathematician, Piano, which has an interesting fact. I'll tell you what interesting fact is followed by this example. We will see that for this example, the function gets a minimum value along every possible direction, but the point x bar is not really a local minimum. This is very interesting and surprising fact. Anyway, I will come back to this scenario. Let me give you one example here, the example of saddle point. Here, one example that we have already seen, x1 square minus x2 square. This example, x1 square minus x2 square In this example, do you know what is going to happen? For this example, if we try to find what is the graph or what is the surface for this function, you will find that its surface will look like the following. That it will look like the seat of an horse. You have the seat like this, and here let me draw out what are the axes. So here is the origin, the point x bar, and at x bar you have the axis. Here you have the location of the axis. This is my axis x1, and here goes the axis x2, axis x2, and here goes the axis z, the function value axis. Fine. And for this seat, you note that if I move along the x2 axis, then you are just visiting the surface of the function only on this curve, right? The function along the entire function reduces along the x2 is this red curve. Fine. And for this red curve, we note that the point 0 0, which is your x bar, is a local maximum. However, if we move along x1, this is precisely this red curve. Fine. And which has a local minimum at the point x bar. And this looks like this surface seat looks like horse's back, right? And from the horse's back, actually, the terminology saddle came, because when you want to step up to horse's back, then you have to put your leg on some settle, and which is called as saddle, and that's why this nomenclature has come out. Anyways, for the function due to piano, with the help of the saddle points definition, that this function, this piano's function, is having a saddle point at the point origin. Fine. X2 square minus 2x1. For this function, we know that consider this, and also you consider x bar. Here x bar is two dimensional, so here you consider the null vector as x bar. Now here we note that gradient of f at the point x bar, you can quickly calculate, you will get a null vector. Therefore it is a stationary point. We note that to check that a given point is a saddle point, at first you have to have the point x bar a stationary point. Then only we move ahead to check that in every possible neighborhood of the point x bar, you have a pair of points x dash and x double dash with the different inequalities. Fine. So here we consider a delta neighborhood, a generic delta neighborhood. Let me consider, and then we will find out points x dash and x double dash in that neighborhood. Fine. So let me take this neighborhood, delta neighborhood here. This is my delta neighborhood. This is my delta. This is my delta neighborhood. Delta is a generic quantity. And in this delta neighborhood of the point x bar, try to find now 2 points x dash and x double dash, such that what you should realize that f of x dash x delta dash is your a point for which it must be less than you have f of x bar. And what is your f of x bar? X bar is nothing but 0, and therefore you find a point x delta dash in this delta neighborhood for which f of x delta dash is negative, and as well you try to find another point x delta double dash for which the function value is positive, or function value is bigger than f of x bar. Now here, due to these two factors, the function is given by these two factors. Can you now find a region in which the function value is negative, and in the complement of that region the function value is positive? Fine. And you note that these two factors, if we equate to 0, then we find that x1 equals to x2 square, the parabola, that parabola, let me just draw out this parabola. This is my parabola x2 square is equal to x1. And also let me draw another parabola which is this parabola. Here is my x2 square is equal to 2x1. Fine. Now we note that the function is negative in this region. If we consider any point in this region, then we note that in this region or here in this dotted region, we note that the function value is negative, right? However, outside of this dotted region, function value is positive, right? And once you have this, then as we know that whatsoever delta you choose, this dotted region is having an intersection and non-dotted region is also having an intersection with your B delta neighborhood. It's not that. To be more precise, let me consider here, here obviously the radius is delta. Let me consider here delta by 2 on x2 axis, and corresponding to this delta by 2, a point, let me try to find a point that lies in the intersection of this line x2 equals to delta by 2 and the dotted region. Fine. And what could be a possible choice? You can find what could be a possible choice. I'm giving a precise value by taking x dash x delta dash. You can choose some other value. I have chosen a particular one, 3 by 4 delta square by 4, and you take delta by 2. Fine. This point, and you have x delta double dash. You can choose a very nice point. Nice point means not with this cumbersome expression like 3 by 4 delta square by 4 and so on. So let me just take outside this dotted region. I can take either this point or here also in the x1 axis you can take delta by 2 equals to 0, any one you take. And let me just take 0 delta by 2. Fine. And accordingly we note that the function value at x delta, how much is the function value, is delta square by 16 times 1/8, and which is a negative quantity. And for x delta double dash you have delta square delta to the power 4 divided by 16, right, which is greater than 0. So here, so for any delta greater than 0, we have this and this belonging to the B delta neighborhood of the point x bar, for which this and this, right? And therefore x bar is really a saddle point of the function f. Fine. So here you note that as delta is a generic value, whatsoever the delta value you take, accordingly you have found a pair of points x delta dash and x delta double dash such that reverse inequalities are happening, and therefore x bar is a saddle point due to the definition. Now let me say a few words about this piano's example. You can have this interesting note that you can have a function which is minimum along every possible direction emanated from the point x bar. As you know, along every direction d, any given direction d, the function f of several variables reduces to a function of one variable, f of x bar plus lambda d. It is a function of lambda only, right? And you can have a function such that along every possible direction d, whatsoever direction d you can choose, whatsoever direction you choose emanated from x bar, along of every possible directions the function might have a local minimum, but the point x bar might not be really a local minimum of the given function f. So piano's example was not just for a saddle point, but it possesses an interesting fact that a function of two or more variables may have a local minima at x bar along every direction emanated from x bar, that is along the directed line, but x bar may not be really a local minimum of the function f. Fine. Once you are writing that it is not really local minimum, you have to give an example with mathematical expressions and with mathematical reasoning. Mathematical reasoning should not move like if this will happen, that will then evidently happen. But nothing is evident in mathematics. So in everything, you have to give a very precise mathematical expression, mathematical equality, mathematical inequality, or mathematical assumptions. Then only you can say your writing is mathematically perfect. Your writing is not only mathematically perfect, your writing is correct rather. Anyway, so for this note, we visit the following problem. See the following example. This problem is very interesting. Although I have worked out this problem, but I'll just hint it out. You let you do it, and accordingly let you find the interest on this problem. Unless you bog down a little, unless you play with certain mathematical expressions, things will not be clear and things will not be interesting to you. So that's why I'm giving at several day with sufficient hint. I'm several giving you homeworks, and you must do those homework very carefully. Otherwise, it will be very difficult to learn this optimization thing. Well, the problem states the following. Fine. However, show that x bar is not a local mean of f, and why is it not coming? For that, the logic is infimum of all these delta d is equal to 0. Fine. And what this result is saying, that the function of one variable along every possible direction d gets a local minimum at the point x bar. So origin, we have to show that origin is a local minimum for every d. You consider f of x bar plus lambda d, and for that function you have to show lambda equal to 0 is a local minimum. That is what this inequality says, right? And what does the latter result says? For the latter result, x bar is not a local mean, that we have already seen, that x bar is really a saddle point, that we have seen. But what do we have to prove in the latter part is that infimum of all these delta d in which you have realized this inequality, infimum of them is equal to 0. What does this geometrically say? It says the following. It says that, you note that if I fix my attention on this direction d, then what does this result says? That you take elongated this direction both the ways, minus infinity as well as um, plus infinity. Here there is no plus and minus infinity in R2 although, but here on the negative side you take, here on the left hand side you take to up to infinity, on the right hand side you take also take up to infinity. And in this direction your reduced function of two variable is reducing to this function of one variable lambda. And then we note that what does this result says, that corresponding to this d you have a delta d. So you have a delta d means you have a length here. This from, let's suppose this my length is from here to here. So this much length is my, so origin to this green point is my delta d. Fine. And for these delta d, so in between this length in between these two green points, here and here, in between these two green points, we'll see that the function value at the point x bar is the minimum most. Fine. And we know that once you vary this d to some other direction, let me consider some other direction, and that direction is something, let's suppose this is my other direction, this is my other direction, say. Okay. And corresponding to this direction, the amount of the length of this delta d might not be same as this length from for this red directed line. So if I just take d1 here and if I take d2 here, so delta d1 might not be equal to, they may be equal but might not be equal to, in general, is delta 2. Fine. So there is a variation. In fact, we will see that there is a variation. And not only that, so therefore we note that this delta d is really a function of delta. It depends on it is really a function of d. It depends on this d. If you vary d, accordingly this delta d gets varied. This amount of length in which you realize this inequality f of x bar plus lambda d is greater than equals to f of x bar, this length gets varied once you vary this d. And if you take minimum most, rather infimum most value of this delta d, that is equal to 0. That is what this result says. And once this is equal, you know that if it is not 0, let's suppose if it is not 0, in that case what will happen, you take delta to be minimum of all these deltas. Fine. All these delta d's, you take this, and what will happen now, then you will see that for this delta, what you will have, f of x bar plus lambda d is greater than equals to f of x bar. This is going to happen for every possible d. This delta will work for every possible d. So for every possible d, you have this for all lambda with modulus of lambda less than delta, and that will essentially say that the point x bar is a local minimum. Is not that? And that is not really the fact here. So as this delta is 0 here, that's why you are not able to find a delta which will work for every possible d. Okay. Anyway, so now let me just hint you out here how to get this result done. As a solution, we note that any d with norm of d is equal to 1 can be can be written as this cos theta sin theta, right? Where theta is in between 0 and pi, then all the directions are visited, because the directions you are visiting with positive and negative direction due to this lambda being negative as well as positive. Fine. Well, so with this d, you note that your function phi of lambda given by f of x bar plus lambda d, this expression goes with, now find that this expression goes with this expression. This is greater than equal to phi of 0. You can find for all lambda such that a modulus of lambda is less than delta of theta. Delta of theta is nothing but delta of d here, because d is characterized by a unique theta in between 0 and pi. And what is the precise expression of delta d? Delta d has this expression for all this, where try to find why this expression is going to come. With this delta theta, this result that phi lambda is greater than phi 0 will be proved, and that will prove the inequality that we require, f of x bar plus lambda d greater than equals to f of x bar for all modulus of lambda less than delta of d. And here you note that infimum of delta theta. I guess by now you know what do we mean by infimum. Is equal to 0. Fine. And the other part, that x bar is not a local minimum, is already proved because it is a saddle point that we have already proved. Fine. Now with this, let me stop the class here. And on the next day, I will continue our discussion with first order sufficient condition of optimality, then second order necessary and sufficient condition of optimality, second order sufficient condition of saddle point as well. So those are the agenda on the next day. Well, thank you. Thank you all for your kind presence.